Fireside, like the science fiction theater. This is what mainly I'm going to talk about. I don't think there's been enough technical content. So I'm going to go through the 33 instructions in the C18 instruction set. And it's a good story. Each instruction has a story to tell. But first, this is the 40th anniversary of Forth, as close as anyone can figure. I actually think the 40th anniversary was in the spring. Near as I can remember, 40 years ago, back in Amsterdam, New York, when I put Forth on an IBM 1130 mini computer, one of the very first mini computers. And that was fun. In fact, it was so much fun that I think 6 months later, maybe about now, I put Forth on the Burroughs 5500, which was a mainframe, which had the Forth stack architecture, which is where I learned about stack architectures, and which didn't ever have any language on it except, as far as I know, Forth and Balgol. Those were the days. Just to review the history a little bit, after Mohasco, and there's still a home furnishings company, you can buy Mohasco carpets. I went to NRAO and programmed telescopes. And then Bess Rather and Ed Conklin and I set up Forth Inc. And we programmed applications and ported Forth for 10 years, very, very happily. And then I got fed up with hardware. I was asked to program applications on a circuit board that somebody developed to run a robot or what have you. And I learned that those circuit boards were very badly designed. They were going out of their way to make it hard for me to do my software, which motivated me to get into hardware and motivated me to go with Novix and design a Forth computer. And then what was it? My cowboy computer.
Computer cowboy. Computer cowboy. Shaboom.
No, before Shaboom there was Bonfire. Anyway, then Shaboom, then the patents, then a flock of little 21-bit microprocessors, and that culminated with the F-21 for Jeff Fox and the I-21 for ITV. And by that time I was fed up. Except for an epiphany when I said I could put more than one of these computers on the same die. I could put maybe 4 or 8. And that led to Seaforth, ultimately, Intellisys. At that time, the patents became valuable and funding became available. And 24 computers. It took a while to make the 24 computers work. And just as soon as we got them to work, it became clear that we could have 40 just as well. So now we have 40. Then there's an amazing amount of ignorance, even in as sophisticated and communicative an industry as Silicon Valley. We finally learned, 6 months ago, we've been making shuttle runs to prove the architecture, to prove the details of the technology. And learned that a shuttle run for a much larger chip didn't cost any more. So we've been throwing away money on a 40 node chip. Now we're going to make a chip which fits the envelope of the pricing of TSMC. No reason not to do that. And I suppose every manufacturer has his own pricing structure, so as we go from one place to another, the chips will change in their size to accommodate that. It is essential we make a couple of shuttle runs before we go into production. You cannot trust the manufacturers to honor their own specifications. You don't really know what's going to happen. It's a crapshoot. That's why it took so long to get the S24. But we are in good shape now. We have 75,000 of those little suckers. We have 10,000 of them in Cupertino, and the others coming down the path. So if you have any inkling to buy some chips, buy some chips. I don't know what the marketing processes are, but this chip, as far as I know, is perfect. There are no, what do we call them?
Programming issues.
Okay.
Violation rules, usage rules.
For instance, this is the J model. The H model, one of the restrictions was you could not have a Micronext loop that was empty. Well, why would you want to do that? But yeah, I've wanted to do that. So it's just nice that it now works. You can have one that's empty. You couldn't have a next loop with a dot in front of the next. These are weird problems, not exactly timing problems ultimately. As far as I know, they're all resolved. You can do anything you want with the instruction set that I'll be talking about, and you're golden. 75,000 chips at 40 computers per chip is a fairly large number of computers. I'm still getting, it's almost ready to go, I guess, my little 3x3 array of S40s, which will give me 360 computers on a board that will run off flashlight battery. That's going to be fun. I'm not sure what I'll do with it. My intent was to put OCAD on it, and I will certainly move in that direction, but I'm tired of putting OCAD on things, and maybe there's something more exciting to do, like sing Seaforth. What else is happening? Not Forth that I know of. There's a bunch of companies that are coming out with multi-core chips. Most of them are, well, all of them are much more expensive than ours.
All of them require a heatsink.
Yeah. It is literally magical that our chips don't require very much power. Bill, you're talking about 20 milliamps for the PIC, and we are 7 milliamps for one of our nodes running flat out. Asleep, we are 1,000 times smaller. We are an ancient technology. 0.18 micron isn't interesting to anyone except us. We like it because it's relatively cheap. It's plenty fast enough until people start using the chip, and pushing is to saying, you know, if it was 50% faster, I'd buy twice as many. We have no motivation to go out there and make yet a better chip. The potential exists for probably maybe a 4 times speed up, 3 or 4 times speed up, by going to the smallest geometries, corresponding reduction in power. But if this isn't enough, it's not worth the trouble. So we'll see.
Yeah, not fair comparison. We run 700 megahertz, it only run 100 megahertz.
That's right.
We run 7 times faster.
And we've got 40 of them running at the same time.
Now, I was just gonna say that, once you get up to too many cores, though, you don't find you don't have enough I/O now. You don't have to start spreading, getting more I/O.
That's right. There's a sweet spot somewhere. It is amazing. Another thing I've learned, two things I can mention. Packaging. It has been a nightmare to try to come up with the right package. We have tried this and we've tried that, and we've got a package now which we like, but Amcor, is it? Might not be willing to provide them to us. Our volume is not large enough, or some nonsense like that. On the other hand, the industry is in severe recession. They probably aren't going to hassle us for a little while. Packaging is hard. Testing is hard. We're programming a test machine so that we can run all our packaged chips, not the wafers themselves, but as we get packaged chips, we can do 100% testing on them at about 2 chips per second. That's going to be fun, just to see them. It's just like you see on How Do They Make It? All these machines doing things, and well, we have a machine doing something for us. The other disturbing issue is ESD protection. It's a bit of a magical black box that is ill-documented, exactly what you need to do to achieve industry standard levels. So we have to work on that. We need better ESD protection, which is why the wrist straps and the grounding wires are particularly important in dealing with these chips. Has anyone burned out one of the chips? You did?
Yeah, I did. Actually, I put a Thunderbolt on my fingertip and it was a serial I/O chip.
Yeah.
The only reason that happened was I was down in Southern California during the Santa Ana wind. I was trying to push the reset button and I slipped.
Okay.
Well, the chip.
I did damage. What was I doing? Oh, I put over voltage into one of the input pins and destroyed the pin. Didn't hurt the chip, but there's this whole spectrum of things that can go wrong. We did have someone run the chip, the 24, I think it was. Yeah, it must have been. In an accelerator beam to test it for radiation hardening. And it didn't do particularly well. It did as badly as any typical commercial chip would do. So there's potential for coming up with a rad-hard version of our chip. Fourth, to stop talking about the chip and talk a little bit about Forth. I was surprised to hear about the standards efforts, 200X. I hadn't. I'm pleased that there's enough interest that someone wants to update the standard, but in just glancing at the list of proposals, none of them are exciting. I would suggest, maybe I actually will suggest, that the standard be broken into 2 levels. The minimal level that qualifies you to say we are standard Forth, and then the mega Forth with all of the bells and whistles and the syntax. Because the standard as it stands is of no interest to me. I'm not going to do all that stuff. But then I'm not going to do all that stuff anyway because I'm working in Color Forth. And Color Forth is not even close to the standard and won't be. We keep encountering Forth people in our peregrinations about the industry. Correct me if I'm wrong, but there's no great resistance to using this chip because you have to program in Forth. That seems to be an old attitude, maybe that it's gone away. If it has, I would argue that it's because the other languages are so detested that Forth doesn't look so bad by comparison. Will we see a renaissance? If this chip is successful, we will. Actually, if you look at if you read about Kurzweil's singularity, the world is going to change any year now, certainly within 10 years. Everything's growing exponentially, and all those exponentials converge around 2020. Something profound is going to happen. One of the things that could happen is a new programming paradigm based on fourth and parallel computers. And it might actually be worth reprogramming all the legacy software. That if we don't reprogram, we'll be a ball and chain on our ankles for the rest of our civilization. And this may be not so much that you got to replace C with fourth, but you got to replace serial with parallel processing, and fourth comes along with that. Fourth is very nice for parallel processing. Oh, a couple more words. I've got 33 instructions to talk about. At a minute each, that'll take a half an hour, so I have a little more time. Lockup, mentioned recently. We thought about lockup and what we might do to prevent it. And the team we had working in Tempe a year or so ago came up with hardware schemes for preventing lockup. They were elaborate and expensive. The thing is, you can't detect lockup. You might think if one computer is reading, its neighbor is reading, they're locked up. Not so. At PowerUp, almost all of the nodes are reading all of their neighbors. Only the boot nodes are actually running. So everybody is reading everybody else. They're all locked up reading. And that's an okay thing, because as soon as somebody is written to and switches from reading to writing, the signals propagate just fine. Perhaps a little less obvious is the case where you've got one node writing and another node, its neighbor, writing to it. So you're thoroughly locked up. But that could easily be the case when you're doing a multi-port write. You're writing to, well, you can't really write to 4 neighbors, but you can write to 3 of your neighbors. And some of those neighbors may be writing back at you. And again, you've got to lock up until somebody switches modes and decides to read. And that's okay. It doesn't hurt you. It doesn't even draw any power. This is a perfectly benign situation. Unless it is unintentional and there is no mechanism for correcting it. One thing we could do, and I've agonized over this considerably, is provide a way for a node to reset its neighbor. Trouble is, that's a lot of circuitry, and it isn't clear it will solve a problem that exists. We haven't had a need to do that yet. Adding all that mechanism for a problem that might exist, and you don't know, you're not making things worse. If I can reset my neighbor in some kind of failure mode or software situation, I might inadvertently reset my neighbor. This is more trouble. This is causing the problem, not resolving it. So that doesn't seem to be a smart thing to do. And this is an issue that perhaps affects the optimum size for the chip. How many nodes should there be in a chip? Yes, an I/O limitation, but also a failure mode. We can reset a chip. That's easy. Resetting 40 nodes at a time maybe is the optimal thing to do. If your system is smaller than that, it's probably not very important. If you have dozens of chips, the ability to reset one might be all the granularity you need. So there's some architectural issues that have not, well, that might be subject to further development. But I'm really pleased with the communication. It works elegantly, simply, and quickly. I heard something about going to sleep. And I heard, I guess, we don't go to sleep. There's no action taken to put a node to sleep. What happens is the node writes to a port, and it doesn't get an acknowledge signal back from that port until someone reads from it. So, no, you don't, you fall asleep. You don't go to sleep. The situation is that no transistors are going to change state until that acknowledge signal comes back. And what could be simpler? What could be, to actually power down a node would take huge transistors. Those huge transistors would have large leakage current. It isn't clear to me that you gain anything by doing that. And we avoid all of that. We avoid all of it by having an asynchronous clocking scheme. And no one else is even talking about doing it that way. So we'll see how it goes. Let's quit philosophizing and look at some details. Does have someone have a pointer? Pointer, thank you. There we go. These are the registers we're going to be talking about. R is the top of the return stack. A is the address register. B is another address register. P is the program counter. I is the instruction word with 4 instructions in it. T is the top of the data stack, and S is the next element on the data stack. That's really all you need to know. That's the architecture. Some of these registers talk to each other, some don't. The first class of instructions, we have 32 potential instructions, divided in 4 classes, each with 8 instructions. 5-bit opcodes. The first are the jump instructions. And the first jump instruction, 0, 0, is semicolon, which is return from subroutine. This is, everyone knows this. Everyone knows all these instructions, but there's still some things to say about them. Return from subroutine. There are 2 modes to that. One is tail recursion, which is probably a terrible thing to use, but if semicolon appears after a call to a word, it's turned into a jump to the word. So you avoid having to push the return address on the stack and pop it back off again. You just save a little bit of trouble. It's also very useful. Can't quite see these words, I'm sorry, but that's a push semicolon. If you have the address on the stack of the place you'd like to go, push it on the return stack and do a semicolon, and you get there. That's a call, right? It's a
It's a computer jump, yeah.
Semicolon is a computed jump, yeah.
okay. Finally, it's useful for a vector jump. If you have a number, small integer number, and you'd like to go to one of the 12 places, you just do the push semicolon and you'll get there. You jump into a table. Hopefully it's a table of jumps instead of a table of calls. All right, that's opcode O.
Increase the size of your font. Display.
Oh, the hex number, 00. I'm sorry?
Make it bigger.
I tried. This is as big as it easily gets.
Doesn't do it?
Hmm?
Control plus? In the web thing, you
Well, I can try, but I already went to the menu and
just hit control and then plus.
That's fun, okay.
Keep going.
hey,
You can go. Go for it.
live and learn.
Okay, stop. That's good, that's good.
Yes, there we go. That's good.
Look at it now.
Okay, then we come to 01. These are hex numbers. Semicolon, colon. Some of you may remember that from Classic 4, it's still in Classic 4? It's a jump, to do a semicolon and then do a colon. You return from somewhere and go somewhere else. So basically what it does is it jumps through R and it saves P and R. And this is where you can interleave two threads. You're executing this thread and you jump to this thread and you return back to this thread where you were and continue. Right. And I think eForth uses that?
Yep.
So it was useful. It's also, because it only differs from semicolon by 1 bit, it was easy to implement. And that is as much a consideration as anything else. We've got a very elaborate, time-sensitive decoding scheme. And I can't do anything I want. These are the things that can be done. 2 is a jump instruction. Of course, you need a jump instruction, right? Well, you need it for tail recursion. You need it for else. But that's about all. I mean, we don't do many jumps. There's no reason to jump somewhere. You might call somewhere, but jumping is rare. If else, then is the conditional. Sometimes I leave out the else. You don't always need it. And you can compute a table of jumps using that instruction so that you can vector yourself somewhere. A lot more efficient than doing any kind of bit testing. And then call, good old call. This is the syntax in ColorForth. A red word and stuff and a semicolon. When you use a green, use the name in green, you get it generates the call. Calls require a memory access. Memory accesses require, what, about 3 times as much, take 3 times longer than an ordinary ALU type instruction. It's prudent to avoid, it's prudent not to use more calls than you really need. Inline code is more efficient.
You should mention the effective slot. Call.
Yes, I should. I should have drawn a picture there. There are 4 slots. If call is in slot 0, the remaining slots are available for the address. If call is in slot 1, you can have another instruction in slot 0, and you have 5, 3, 8 bits for address. If call is in slot 2, you have 3 bits for address. And any bits that you don't pick out of the instruction word come out of the program counter. So you can jump within these little pages if that's convenient. It actually took extra work to make call work in slot 2. That was one of the fairly recent changes. All this helps. Micronext.
The Micronext is 4.
Yeah.
It's its own instruction.
Oh, okay. Micronext used to be a version of Next in slot 3, but this is better and it was easier to decode. A delay loop. You say 4 Micronext, having a number on the stack, which 4 will push onto the return stack. Micronext will just branch back to it. Micronext takes a little bit longer, not much, a little bit longer than an ordinary instruction. This is a delay loop. It's got granularity of 1 instruction time. A multiply is basically putting a plus star, which is a multiply step, inside a Micronext loop. It's 1 word. It just grinds up your multiply until it's finished. You can multiply by 4 bits, 6 bits, 18 bits, whatever is suitable. You need more code around this. This is not sufficient in itself, especially if you're going to do a signed multiply. But this is the basic multiply loop. Likewise, shifting. You can shift left or shift right using a Micronext loop. It takes 2 instructions per iteration. If you string out a whole lot of 2 stars, 2 stars, 2 stars, it's faster, but it's also bigger. It's your choice. And finally, these are called port pumps. It's a little loop that does a fetch and a store. Now, the reason we have 2 address registers, A and B, is to permit this to happen. Actually, we don't use A and B quite as often as we might. For instance, here you're doing an incrementing fetch from A and a store to B. So you might be fetching something out of your RAM and sending it to a port. That's all you need to do port communication. The store B instruction will wait until the operation is complete, and then we'll continue. To go the, let's see. This incrementing fetch, the increment is suppressed if A was pointing at a port. So this would be suitable for going from one port to another port. Now here's the converse of that is to fetch from B and incrementing store to what A is pointing out. I'm sure there's a difference between them. You use the one that works for you. We might have some of these in ROM for no good reason. It's only one word. Here's a sleeper. This is even more of a sleeper. If you're executing your code from a port, you can do a fetch P plus using the program counter as one of your address registers. And it will not be incremented if it's coming from a port. And then do a store somewhere else to another port or into memory. Conversely, you might do a fetch from a port or from memory, and then a store P plus to the port from which you're executing this instruction word. We've got 4 instructions per word. Here we're using 3 of them in a loop. So that instruction is resident in the instruction word, does not need to be refetched. The only cost is the fetch and store of the data words. The whole thing was a sleeper. It was kind of designed in from the beginning, but it's much, much more valuable than we appreciated at the time. And then there's good old next. For next, just to be complete, has a count on the return stack, which is counted down to 0. And it's a decrement and count instruction. Countdown loops. As distinct from micronext, you can have more than 3 instructions within the loop. Here's a code necessary to do a match, which is the code I'll be using to do lookups in ColorForth. You have on the stack is the word you're trying to match. You do an incrementing fetch and an over OR to do an exclusive OR and a compare. And if the result was 0, you found a match, jump on 0, and you come to here, and then you've got your match. If the result was not 0, you throw away the comparison, and you do a next to go back to the beginning. The magic of ColorForth is this yellow word swap, which is executed at compile time and swaps the 2 addresses, one from for and one from if, that are on the stack at compile time. You can do the equivalent in VentureForth. It's just much uglier.
Use while instead of if.
Yeah, there's a lot of constructs. And here's the code for /mod. This is, as with the multiply, this is the heart of a divide operator. You're going to do it so many times. You do over plus. So you do a trial subtract. And if the subtract came out positive, come here. If it was negative, you come here. You throw away the result of the subtract and do a 2 star. 2 star shifts your dividend left, shifts in a 0 into the quotient, into what will be the quotient. In the other case, you do a nip. And this is the code for nip, over or. And it's nice. You pull over the number, exclusive OR it with what's on top of the stack, then exclusive OR it again with the number itself. The number's gone away and you've got the thing that was on the top of the stack still there. It's not the only way of doing it, but it's the neatest way. Then you do a minus, one's complement, 2 star, which shifts in a 0, another minus, which makes it back into a 1, and you've shifted a 1 into the stack. And then you repeat that. There's 2 nexts, a next here and a next here. You do whichever one is appropriate. Again, you need more code around this in order to set yourself up to do the divide. It requires that the divisor be negative so that the add is really a subtract. And it requires you worrying about justifying left or right and sign manipulation. But basically, that's the code necessary. One line of code. I hope all of these are one line of code. Then there's if, jump at 0. If then, if you want to test for unequal, you do an or, if then. Minus if is similar, except it's looking at the sign bit instead of all the bits. If is an expensive instruction. It requires a 0 test on a number that's in A. And we have a clever way of doing that without having a hierarchy of 15 AND gates. Absolute value. Minus if one's complement and add 1, and you've got it. And this all fits in 2 words because you need 1 word for the literal 1. Max is this. Min is this. You do a trial subtract and either throw something away or add it back in, and you get the maximum of 2 or the minimum of 2. Every time you see code like this, you want to be really careful to check that these haven't gotten exchanged and you aren't doing a min instead of a max, because they're very similar. Okay. Those are the jump type instructions. Here are the memory fetch instructions. This is fetch P plus. Now, another thing to consider is opcodes that are divisible by 4 can reside in slot 3. And we've picked the most common opcodes to have that characteristic. This is literal fetch. Because it can be in slot 3, you can fetch 4 literals in 1 word. Fetch, 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 fetch. Which is not an unreasonable way of getting stuff onto the stack. You can fetch a number. You can fetch 4 numbers. You can name a constant. We don't have a word as classic fourth does of constant. You just say colon, well, pi, define pi as 3.14, semicolon, and call pi when you need it. It takes 2 slots. 1 for the number and 1 for the code. If you define this word and then reference it in yellow, you actually put a literal in the middle of your inline code rather than having to do a call to get it. You can add a number by defining a word that just picks up the number and doesn't add. A dot add. So that is the literal fetch operator. As I said, it works beautifully from a port. You just sit on the port until your neighbor gives you the value of the literal which you're asking him to do. fetch plus fetches using the address in the A register and increments the A register. This is how you can check some memory. Put a 0 in the stack, and for 63 times, do a fetch plus and an add and a micronext.
You might also mention that the RAM address wraps from the top of RAM back to the bottom of RAM, so that if you use one of these incrementing pointers in RAM, you're going to stay in RAM.
Good point. Or if you're in ROM and you're doing it, if you're checksumming ROM, it would wrap around there too. 64 words of RAM and 64 words of ROM. That's because that's much space as was conveniently available. And it's also a programming discipline feature that if you get too carried away with writing big programs, they aren't going to fit. Here's the same thing with the B register, fetch through B. It doesn't increment. For instance, if you want to read the status register, you stick the address IO in B. That's something that almost always resides in B anyway. And do a fetch B. Anxious to get down to fetch. Here we are, fetch. In VentureForce, this is known as fetch A. Pedantic people figured it would be better to have symmetry in the instruction set and explicitly require you to indicate the A register. I just think that is unnecessary. Clutters up the code. Fetch fetches through A, and you can do the same kind of thing with the to get the status register or anything else you want to fetch from an address. And then here's good old store P plus. You can store the contents at the top of the stack into a port if you are executing from that port. That's the major use of it. But also you can make a inline variable, if you will. Define X so that there's an initialization value there. And when you say X, you will get back 100. Or you can say X store, which will fetch the instruction from this location, throw it away, and then store a value into the next location, which is where that 100 resided. So it's a neat way of fetching and storing a variable without having to set an address register first. You're using the program counter in both cases to do the fetching and the storing.
Standard forth called a value.
Called a value?
Instead of variables or values, where you fetch them by name.
That's right. This
and
is
then use the prefix TO to
Yep.
Store it. That's equivalent to what we've done, what Peter did.
This was Michael's Russian programmer who has been very creative. We don't even know if there's things about this instruction set no one has discovered yet, but it's a fun instruction set. All right, here's a store plus. It stores in increments, suitable for filling memory or executing from port. Here's a store B, which is not increment, but it does store into the address loaded into the B register. The B register is only 10 bits long. It isn't a real number. You can't read it back. The A register is 18 bits long and you can read it back. If you want to set I/O pins, if a port has 2 I/O pins, they're typically going to be in bits 17 and 16 and bits 1 and 0. And you can set these pins to be either to write a 1 to a pin, to write a 0 to a pin, to read back the value of a pin, to tri-state a pin, or to have a weak pull down on a pin. So there's a number of programmable characteristics. If you want to set the pins 30003, store B will do it, presuming that B is set to the IOCS. If you want to reset 3 pins, it would be a 200 is the constant you use. And this is in color fourth. I'm not sure what happens in venture fourth because sometimes the patterns are different. And then ordinary store, you just set an I/O pin providing the register A has been set to the IOCS register. ALU instructions. All right, we got some are unary, some are binary. This is the multiply step instruction. 10. It can be low. It can be in slot 3. A 4-bit multiply would be 4 of them in line, with a dot in between them. The dot is necessary before a add instruction in order to let the carry propagate properly. An n-bit multiply, I've shown you before. This is the fastest way. You need to have a dot in front of the first star plus star. Thereafter, the micronex will provide the necessary delay for settling. This is the code for an unsigned integer multiply. I think I would always test this.
You cannot push into the slot 3, so it's done automatically.
The dot.
Yeah. It's not slot 3.
Good point. Excellent point.
You also might mention that it's become double on the S4.
When it's using the register.
Oh, okay. If you know the 24, you don't know the 40. This is an 18 by 18 multiply, which produces a 36-bit product. It uses the A register to accumulate the low order part of the product.
Part of the thing, and it does a double shift between T and A.
Conceivably, plus star could be used as a shift operator if you set it up right. All right, 2 star. This is a very simple operator. Shift left, shift in a 0. It lets you do these simple multiplies. Multiply by 3 by duplicating the top of the stack, shifting it left, and then adding. And then you multiply by 3, multiply by 5 or 6 or 7. If you want, you can look at your neighbor ports and see if they're reading from you or writing to you. And you do that by reading the port with a fetch B and then doing 2 stars to shift the bit you want into the signed bit position so you can use a minus if on it.
Read IOCS, not the port. If you read the port, you go to sleep. IOCS is where the status of your neighbor ports is found.
Quite right. And likewise, typically the port statuses are 2 bits apart, so you need 2 star in between things. If you set it up really carefully, 2 star minus if is all in the same word and doesn't cost you much. 2/ is much less useful. It divides by 2. It's a signed right shift, so the signed bit is propagated. That's true because it's easier to get rid of a signed bit you didn't want than to create one that you did want. So, here's one complement operator. It's surprisingly useful, especially for subtract. If you want to test for positive instead of for negative, you just do a minus if. To negate, you do a minus 1+. To subtract, now you get some clever things. To subtract T from S, normally you want to subtract S from T.
The other way.
Subtract T from S. Right. You do a minus and then a plus. But you're going to be off by 1. So keep that in mind. You fix it up later. You don't always have to add 1. To subtract S from T, there is a more elegant way of doing it. Minus plus minus will get you the correct result. So henceforth, I plan to invert my normal order of thinking about who gets subtracted from whom. To construct a -1, use a dupe or minus. Dupe or will give you a 0, and the minus will make it a -1. If you want to preserve the top of the stack, you need another dupe. If you want a -2, you do a dupe.
XOR, dupe, XOR. Dupe
Or just gives you this original value.
Or is XOR here, Bill.
Okay,
Excuse me,
There
yes.
is only an XOR.
okay.
As with the fetch A, an extra character doesn't convey any useful information, except in this case. -2 would be a construct a -1 and shift left 1. +1 would be construct a -1, shift left, and then complement. But there's no really advantage to that particular construct. Add, only thing interesting about add is you must have a dot or some kind of delay in front of it. This is the add with carry instruction. If you have set P9, the ninth bit 9 of the P register, that is a little cheat that lets us do something a little bit different. In this case, to add the carry bit into include the carry bit in the add operation and save the carry bit when you're finished. It's great for multiple precision arithmetic. It's a lot of trouble to actually use. There's ways of retrieving the carry should you care about it. And excellent operator for masking things.
May I ask you one question?
Absolutely.
Well, why did you choose the 18-bit instead of 16-bit or 24?
Back in the old days, there were 18-bit memories because Macs used a parity bit.
Fast is very fast. The fastest RAMs for 18 bits still are because of the parity bits.
But
Okay, the reason I ask that question is when you duplicate this IO, say a 16-bit or even much for 8-bit.
it's okay.
So you might have to, sacrifice something.
Oh, it's all like, look at the code.
18 bits, 16 bits is really pretty tight. A lot of numbers fit between 16 and 18 bits, so it helps. This is a clever code. If t was the power of 2, it returns a 0. And I won't explain exactly how it works, but basically, if you have an 8, you subtract 7 from it. Or you get a 7 and then you add it together and you get nothing. It's one of these sleepers. Here's the exclusive OR. This is you could once complement something by exclusive ORing with 3FFFF. And one of the things you've got to learn if you're going to work with the C18 is you have to roll off 4 Fs and you're speaking 3FFFF. That's you can change the sign bit with a 20000. Inclusive OR is easily computed with over, minus, and OR, 4 instructions. The opposite is not true. You can't really, it's harder to get an exclusive OR from an inclusive OR. NIP is over or. Drop, just throw something away. There's another way you can do NIP, and that is to do a push drop pop. That uses the return stack instead of the data stack, depending on what your trade-offs are. Dupe makes a copy of the top of the stack. Square a number with dupe star. Cube a number with dupe star star. Pop fetches something from the return stack. It's often called rfrom or I, not quite I. Over fetches S. Working copy of 2 numbers is over.
Chuck, you might mention that because our nodes are small, sometimes we only care about the top 2 items on the stack. When that is the case, over is the same as swap.
That's right.
Because over is place of swap.
The stack is circular. There's 10 entries on the data stack. You can be really sloppy. You can leave things hanging on the stack and it makes absolutely no difference. Drop is not used near as much as it would be in a classic fourth situation. And that makes over almost equivalent to swap. And that was deliberate. Over seemed a more useful operator than swap. And we didn't have room for both. Here's A, which fetches the contents of the A register. So the A register is a temporary location if you want to put something in it and fetch it back. Dot does nothing. It really, really does nothing. It's a very low energy instruction. It does create a delay. If you're going to store something in the I/O register, if you're going to set a pin, you might want to put a dot and then reset a pin. This will give you not your minimal output pulse, but the next most minimal output pulse. So you've got time. It's useful for timing control. Delay loops, you can have 4 micronext, 4 dot micronext, 4 dot dot micronext, 4 dot 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 micronext, depending on the granularity that you want out of the delay. Push is something on the return stack. 4 is defined as push, begin. If you want to decrement a non-zero number, you can push it on the return stack and do a next and pop it off. That's a singularly clumsy way of doing something I've never managed to do. If you want to clip something using max and min, you have a lower limit and an upper limit on the stack. You push the upper limit away, do a max, and pop it back and do a min. It's an elegant combination. B-store stores an address in B. B-store stores an address in B. Store B stores something in the address already in B. It's potential for, not only potential for confusion, great confusion. I make that mistake all the time. A store stores something in A. If you really want a clean swap, the nicest way of doing it is push A store, pop A. But that does require that you have used the return stack location and you've destroyed A. So you'd like to avoid that. And so there we are, 33 instructions, the 33rd being add with carry. I keep this document because it's a useful reference. I can't always remember how to do an inclusive or how to do the is T a power of 2 trick. So I hope to expand this into a number of one-line coding tricks that, at least for my advantage, if no one else. Not a whole lot of people are using ColorForth. VentureForth has the same instruction set, of course, with different syntax.
We have a few minutes for questions, but not many, and then we need to be on the other side of the door. I wanted to say that we'll rendezvous outside and discuss dinner arrangements.
How about directions?
There are maps available for the
Okay,
dimensionality.
who hasn't had a chance to ask their question?
In the chip spec.
Questions and stuff, and then we'll.
We've got a few minutes. We need to pack up, and I think within 15 minutes we need to be out.
So there was a warning about having too many cores.
Say that again, adding too many.
In the Jeep version spec warning, there was a warning about not having very many cores without doing any I/O. Oh, on the loop.
Howard, yeah.
Was that an issue?
We don't know. It might be.
It changes the speed. Does it get warmer?
The latest version has heavier power buses, so maybe that problem's been ameliorated. It's just something to keep in mind if you get in a very weird situation, you might look into it.
Part of that, you said an asynchronous clocking scheme would help. What's that asynchronous odd?
Each node is running its own ring oscillator to do timing. So all the nodes are really running slightly different speeds I would say a few percent, but somebody said it could be 10%.
It depends on the video code, you can see very slight difference because of variances in instructions. But it's not really that bad.
And you might cool a chip and see if it makes any difference. Put an ice cube on it or something. This? I've got it on a flash here if you want to copy it.
Yeah, if Chuck will send
Oh,
it to Dave, and if all of you speakers will send your stuff to Dave or to me, it'll be up on the web soon.
Fair enough.
Since this is all starting to snowball and come to fruition at long last, and since I'm currently on the figured I might actually spend some time actually making boards on which the inlet chips come mounted. I've not been able to get availability or pricing information. Is there somebody here down at the
Marketing guy?
Chet Brown was here. Dylan.
Dylan and Chet are both gone. Send email to me, or to John Rival.
No, not to me, Charlie. Moderator,
Yeah.
moderator.
Yeah, none of us are authorized to speak to that. Speculation has the chips in quantity at $20, something like that.
I did an article,
Uh,
by Chet a couple days ago that said 50, I don't know all that.
But
But-
if you want the development kit, just use the emulator, develop something that looks interesting and send it in, and they'll send you an emulator the next day.
The simulator, yeah, right,
Um,
fourth drive.
do we know what the evaluation kit costs?
I don't, really,
The evaluation,
Okay.
It's $4.99 on the website.
but if you have something that looks really interesting, he'll send you one the next day.
You can make a deal.
oh, yeah.
Okay, well, thank you for listening. 40 years and counting. Amazing.